If you haven't watched the video on ionic strength, go do that right now before you watch this video. It's really important that we have that idea down. Okay, now in that video I made a big point that if we have a bunch of ions present in our solution, then we'd be making a mistake to think that they're only interacting with things that came from the same parent molecule. They're going to be interacting with any other ions present in the solution. And you can kind of picture that this means that we might actually increase or decrease how well things are going to dissolve or how well they're going to stay separated from their parent. For example, if we have a weak acid, some of the time it's going to stay associated, some of the time it's dissociated. Well, if it's sticking really well to the water molecules and it's having a helping effect because of all these plus charges and minus charges helping to stabilize the now dissociated ion, then you might actually increase the concentration of something. That's what we're talking about with activity coefficients. So what we're going to do here is we're going to take our actual concentration in terms of the number of atoms, molecules, ions, whatever. But we're going to multiply it by some coefficient in order to see what sort of an impact that's going to have on how well it stays apart. And that's going to be something that we're going to call activity. Now, activity should be plugged in most cases for the equations that we're accustomed to using. Now, here you see the activity coefficient table for a whole lot of ions in aqueous solution, and it's specifying 25 degrees Celsius. So this will be fairly applicable for most of our laboratory work. Now, you'll notice that each of these sections are sorted by charge, plus or minus 1, plus or minus 2, and 3, and 4 for a couple of our ions. Let me get rid of that ink because it's kind of getting in the way. Here we are. Now, the sorting here doesn't seem to make a lot of sense when you take a first glance at it. In fact, it looks a little bit like a mess. But let me highlight something. What we're focusing on is how big the ions are. So H plus is obviously going to be our smallest ion. It's basically just the proton. And then for some of these, they end up looking bigger. Now, you might say to yourself, wait a minute though. That doesn't make any sense. How could H plus have an ion size that makes it at the top of this scale, and yet you just said it's the smallest of these actual particles? Well, simply put, and the book will go into some explanation of this as well, we're not caring about the ion itself. What we're caring about is its solvated ionic atmosphere and how big its area of influence is, basically. So you can kind of think of it as being like that tiny little island nation with a massive navy. They may be tiny, but they have a really big sphere of influence. That's the kind of thing we're talking about with ion size in this case. So there's a little bit of experience that comes with that. Just make sure you can find some of the really common ones. Our halides are mostly in this group. Citrate's an important one. I'm not going to circle every one of them, but get a little bit accustomed to finding the ones you care about. And you'll notice that if we started to dilute strength, our total ionic strength that we saw in the previous slide, activity coefficients in this case are going to be pretty close to 1. As we get more and more concentration, these activity coefficients get smaller and smaller. Now, what does that actually tell us, though? Because there's something a little bit confusing hiding here that a lot of people miss when they look at it. Let me just say that our concentration, let's go for, let's say that it's 0.05. And that's our analyte. Let's say that the ionic concentration, though, is going to be about double that. Let's just say that it's going to have 1, 0. So we come over here to the table. We find our 0.1. We come down and we look for our analyte for each of our ions, and we say, okay, let's just say that I'm talking about H+. For that ion, we're going to have 0.83 as its activity coefficient. So if I'm doing the activity of H+, I'm going to have my concentration that I just listed, 0.05. Oops. And then for my activity coefficient right here, I'm going to put in that 0.83. And we're going to grab our calculator, and we're going to say we had that 0.05 times, times 0.83, it's going to be acting like the concentration is only 0.0415. That's its activity. Then you might say, oh great, so it acts like there's less of it there. That should make it have less of an impact. It's actually going to be the opposite effect a lot of the time. What we're saying is that it acts like there isn't as much there. So if we're talking about how well something can dissolve, for example, and we're talking about solubility, remember that if it's at high concentration, it stops dissolving. Now it's acting like it's got a smaller concentration in terms of activity. In other words, you can get more of it to dissolve because the activity is lower, and that's what you're actually plugging in for your equation. Now that's very much the opposite of what we'd expect. What we're saying is basically that if I have something that's slightly soluble, sitting here as a solid in the bottom of my beaker, and I start dumping in some sodium chloride, I can actually get more of this to dissolve? Yeah. Now here's the reason why. Think about what we just described in the previous video. We're going to have plus charges, we're going to have minus charges, and these are full-size charges. What did the water molecule have? Well, it had that partial negative on the oxygen side, and it has that partial positive over here on the two hydrogens. In other words, we just went from it sticking to partial charges to now sticking to full-size charges that are sitting here stabilized in the solution. So if there's enough water molecules to help keep these ions apart, and enough to keep these ions from getting in and bumping into each other again, then we're going to actually do a better job of getting things to dissolve and dissociate. So in this concentration range, we're actually going to be able to amplify how well things dissolve, because it's almost like there's little tractor beams helping to pull these solids into solution. But once all the water molecules end up being busy, we're still not going to be able to keep our counterions dissolved and dissociated. And then, of course, the solubility is going to crash out again. Now, that's what's true for ions. But what if we have something that's a little bit less ionic or a little bit less polar? We'll consider that here in a real-world example in our next video. But let me go ahead and show a more detailed version of this. It's always good for us to be able to say, where did the value actually come from? And this is the equation that you'll find in your book that we use to help determine our activity coefficients. That said, I think it's pretty unlikely that we're ever going to use this equation. I just wanted you to see where it was coming from. And you can see here that we have charge and we have size for the ion. So as charge increases, activity coefficients are going to increase as well. And boy, did we see they're going to get smaller. And you can see that effect. I had to fix that by saying smaller because of that square. See that as we look down a column, when we get to higher concentrations, it jumps down very dramatically. So if we're just looking at the 800 picometer, so that our ion size, A, stays constant, 800, 800, we'll point at the 900 because it's the closest we have on that one, and I'm not going to worry about down here. Or we can be looking at the 500s. You can see that we go down pretty dramatically as we increase the charge. That means we're going to have a bigger effect. And you can see here that our ion size is going to be doing something very similar. As we get to bigger ions, we see a bigger effect. In other words, a smaller number. So that's basically what we're talking about when we talk about our activity coefficients.